All right, so we're on the intellabs.github.io/kafl/tutorials page here. And under installation, it kind of walks through what's required, right? Intel PT based processor. If you're on Linux, you can run a command to check. There's different ways of installing it. The way I installed it is I just installed the latest Ubuntu on a host, and then once I installed Ubuntu on the host, I installed the required software packages here, and then you clone the KAFL repo. You go into the KAFL repo, you run make deploy. This will do things like install the patched Linux headers um, and patched KVM on your system so that when you reboot your machine, it'll load into the patched Linux. So you install, a standard Ubuntu Linux installation, and then KAFL will handle downloading the patches and applying the patches such that when you reboot, you'll reboot into the patched Linux. There's some stuff here on how you can, check what changes are going to be made first before continuing. But really, you're just going to, install it. And then once it's installed, you can reboot. Now, before we continue with KAFL, we're going to set up the disk we're going to use for fuzzing. Now, back to my kind of diagram we had here. Patch QEMU, right? It's going to be fuzzing a target, with what the fuzz, that target that it fuzzes and emulates is that kind of .mem and .state, I think it is, that you take using RinDebug. Using kernel debugging, we took a snapshot of the memory and CPU state of the guest that gets serialized to disk, and what the fuzz will kind of execute that. With patched QEMU, you're running whatever QEMU runs. In our case, we're going to boot it off a QCal2 disk. This is a disk just like a VHD or VHDX. So if you followed along on the, there's actually a Windows Target kind of tutorial on how to fuzz a driver, for example, under WinAFL. I mean, under under KAFL. But how they fuzz it, how they set up QEMU is they use like Vagrant and that to automatically download a Windows 10 ISO image and provision it and stuff like that. I like to provision the disk myself, not using Vagrant and things like that, because it gives us more fine-grained control over the guest. So what I do instead is I have a Windows VM, right? This is using just a VHD. So you can see it's using virttest.vhd here. Pretty much that. I create a VM. In this case, I'm using Hyper-V, but you can use VMware or VirtualBox as well. You create the disk. If you're using Hyper-V, just a VHD. I think you could do VHDX as well, but I prefer just using a VHD. And I set up the guest in here. So what do I mean by set up the guest? Well, set it up for fuzzing, right? What do we need for fuzzing? In this case, I'm using a Windows Server ISO, which is why you see that there's no GUI. It's just this kind of command prompt. I'm using a Windows Server image because, well, if we're fuzzing on a snapshot, right, the less things that are running in the background, the better. So by using a server build of Windows, I eliminate the GUI and some extra processes and stuff that would have been running in the background. So it's solely for performance reasons. I've got EVT fuzz here. I've got WEVT service here. And I set it up for fuzzing, but actually I should go through EVT fuzz because our harness is going to be different now, right? Our harness has to work with KAFL. It has to work with KAFL to tell it how to snapshot and restore and things like that. And we no longer have to redirect disk access to memory. So I've got a custom version of our EVT fuzzer, our WEVT service fuzzer that I made that can interface with KAFL. So let me walk through that now. So We still use detours for a couple things, um, because we're still fuzzing an interface that expects to be called over RPC, but we're not calling it via RPC. Under Nix, we actually could. Since it does full system emulation, we could call the function over RPC, but that would we don't need to go that far out because that's just going to incur more of a performance impact and it's not required. We do include a new Nix header, which includes some definitions for Nix, primarily around the use of hypercalls. Because the way it works is when you want to interface with KAFL, right? Say we're running our fuzzer, or our harness, I should say, evtfuzz.exe. This is running under the patched QEMU, right? Patched QEMU is running, it's actually running the target OS, which is going to be a Windows Server in my case, and that's running my EVT fuzz. My EVT fuzz has to talk to Nix to tell it when to snapshot, when to restore, and certain other things. The way that works is EVT fuzz can interface with it using VM call x86 CPU instruction. This VM call will be emulated by QEMU in its CPU handler. We'll have a VM call handler, and that will check for certain VM call values, one of which will be a magic kind of KAFL VM call value. And when it sees that the guest executed this value, it'll pass it off to like the patched KVM, and that'll be all kind of passed in Nix. So when we want a snapshot, there's a magic VM call values that we set in certain registers to tell KAFL to snapshot. When we're done executing and we want to restore, we tell Nix that we want to restore using a different hypercall. Kind of all flows through between our harness and Nix through these hypercall values. So they all get kind of defined in this header file. You can see that a KAFL hypercall, the RAX register will always have this KAFL RAX ID value, but then additional registers like RBX and RCX will contain provided values. And those provided values are what sets a differentiation between telling Nix to snapshot or to restore or that a crash happened and things like that. And this is actually implemented in assembly because building this on Windows, there's no real kind of VM call intrinsic that we can use. So this KFL VM call func, I defined up here as an extern function, and that's actually implemented in assembly here. So I've got a raw.asm file here called KAFL VM call func is defined as a public function or procedure. And it just does the VM call. It backs up certain registers, sets the provided registers, assuming that you're getting 3 arguments here, which is supposed to be REX, RBX, and RCX. But it's a fast call, so it's actually going to be provided in RCX, RDX, R8, right? So my ASM file here will grab the first 3 parameters, RCX, RDX, R8, put them in the expected registers that Nix expects. So RCX is the first parameter, and this first parameter is going to be this NR value, which is this hypercall KAFL RAX ID. This is expected to go in the RAX register, so I move it into RAX. And then the second parameter is supposed to be RBX, and the third one's supposed to be RCX. Do the VM call so that Nix can pass our values and do whatever it needs to do. Restore the registers and return. I implemented it in assembly. Now this nix.h header file actually comes from the KAFL repository. However, the KAFL repository has it defined with like this command here that I have in comments because it's expected to be built on Linux using something like the minjw cross compiler and things like that. I don't want to cross-compile this on Linux for Windows, so I instead converted it to be compatible with building directly on Windows for 64-bit targets. And since I'm using the MSVC compilers, they don't support inline assembly, which is why I have this separate assembly file. If I was building this with Rust or with a LLVM or Clang-based compiler, I could use inline assembly. But MSVC for 64-bit does not support it, so we have a separate file. Either way, the main point here is that we interface from our harness to NICs using hypercalls, using the VM call instruction. And our harness kind of looks like this now. So I've got some definitions that we don't need to worry about. Let's start with main. We'll start from main. What do? We have hprintf. Hprintf is our own function that uses a hypercall to print this message onto the NICS console. So when you kick off a fuzzing session in NICS, you'll be running that on the Linux machine, right? With the patched Linux and the patched QEMU. And anytime anything in your guest does a hprintf, you will see that message in the fuzz session on your host. So it's just a way of, instead of printing to the console in the guest, which you won't really see, it prints off to the NICS console. So we can actually see this output in our fuzz session. Note that, however, it's not going to start. The way it does it is it'll run your target until it gets to the snapshot point, and then it'll fuzz. So it'll be like this. It'll run the target, then there'll be a snapshot in the target, and then it'll do things, and there'll be a restore. So the fuzzing is happening pretty much at this level, the snapshot and restore part, right? But it will run the target, boot the target from scratch, and load in, the main of your target and all that until it hits snapshot. And then it'll do its thing, and when it hits restore, it goes back to snapshot. So our main just prints off that it's initializing, calls init, right? Init, what does that do? It adds an exception handler. Why? There's two main ways you can tell KAFL that a crash happened. If we want to detect crashes, we need to tell NICS when a crash happens. And there's two ways of doing that. One is pass address of function. And when that function is hit, it says that a crash happens. When hit equals to crash. So, for example, you might say crash function is ke bug check 2, right? If you're fuzzing the kernel, you may tell NICS that when the ke bug check 2 function in the Windows NT kernel is hit, that means a crash has happened. You can tell it like this. You just pass it the symbol name or the address. You pass it the address of the function that if KAFL ever sees that address being hit, it's going to assume that a crash happened. The other method that can happen, the other way you can detect crashes is by explicitly saying a crash happened via a hypercall. There's a hypercall we can do that tells NICS a crash happened. So we can do something like KFL hypercall crash. And when we execute this code, it'll do a special hypercall that tells NICS, hey, a crash just happened. So two primary ways. Pass it the function that when executed, KAFL assumes a crash happened. Or two, we explicitly tell KAFL a crash happens via a hypercall. We're doing it this second way. And the way we're doing it this second way is that we're installing an exception handler. This vectored exception handler is not like a C++ exception handler. This vectored exception handler will handle and get called when memory corruption happens, any sort of usual crash related exception will happen. Page faults, segmentation faults, all that type of thing. And what we're doing is we're passing it the address of our function that's going to be the handler, exc underscore handle. This function, what it does is it gets the exception code and it checks to make sure that if the exception code is one relating to a crash, because we can be called an exception handler for multiple reasons. For example, one might be a guard page being hit, but that might not be a crash. That might be the stack about to dynamically grow itself. So we check the exception code for known crash-related code values, things like access violations or illegal instructions or stack overflows, right? And if one of these are the exception code, then we call panic. And panic is a function that uses a hypercall to tell KAFL that we crashed, that a crash happened. And then it just goes into an infinite loop. It goes into an infinite loop because what should happen when we report a crash is that KFL should restore us back to the start of the snapshot for the next fuzz case, right? So this is the method we use to tell KAFL when crashes happen. So we install the exception handler, then we do our normal things that we need to do for fuzzing. We load the target DLL. We use detours to hook the RPC related functions that we need to handle, RPC impersonate client and wait for init, all the normal things. In here, we're still hooking anti-create file. This isn't actually needed. I could actually remove this. It's just kind of left over, but it doesn't matter. My anti-create file, it's all it's doing is caching the handles so that when you do reset state yourself, you can go through and close the cached handles and stuff, but it's not needed. It's kind of left over. I could just delete this and it'd be fine. Then we set the offsets, which are going to be based on whatever version of WEVT service you're using to obtain the function pointers for registered log query. The constructor and destructor we don't actually need because that was for resetting as well. It's just left over. Same with things like G service and that, right? It's not really needed, but they're still there. We do still call global init to do the global initialization, the one-time initialization stuff. Once that's done, we go down. We call agent init. Agent init, this is a KFL specific thing. We do acquire and release right after each other. This is an initial handshake with KAFL, and these are documented on KAFL's hypercall API page, where it kind of walks through the different APIs and what they are. After the handshake, we tell KAFL that we're running in 64-bit mode. We get the host config and print off some things. Doesn't really, it's not really important. We allocate the buffer that's going to be used for fuzzing, and we get the buffer size from the host config. So when you start KAFL, you can tell KAFL what the maximum input buffer size you want to support is. And in this case, that information gets passed to our harness via this hypercall. And so our harness allocates an input buffer based on the value we set at fuzz time. So if we want to fuzz with one size buffer, we can set that off. And then if we go, you know what, I want to fuzz with a larger buffer, I don't have to modify my harness. I can just restart the KAFL fuzz session, take a new snapshot, but provide a different buffer size. It's not hard-coded in the harness. Once that's allocated, I mem set it. I also mark it as volatile just to make sure the compiler doesn't optimize out this buffer. because this buffer is obtaining contents from outside its own program, right? It's coming from Nix. So I just want to make sure that that does not get optimized out. I mem set it to 0 explicitly just to make sure it's all paged in. And I use virtual lock to also make sure that the pages stay present and don't get paged out. I call get payload with the payload buffer address to Nix. So Nix knows the address of the buffer in my harness that's going to receive the input. I filter on CR3. So I use this submit CR3 hypercall. So what this means is that for coverage, Nix is only going to get coverage when it's associated with the CR3 of my current process. And that's because we're fuzzing entirely in our own process, right? We've loaded the target WEVT service in our own process space. So when we're executing the target functions, we should have the same CR3. So we can filter on CR3 just to minimize any noise from being included in coverage. We submit the magic and the version for Nix that we're using. So Nix has undergone a few patches over time, which affects its APIs. So using a special hypercall, you can tell Nix what version you're working with or what version you're expecting, so that if you're fuzzing with a different version of KFL on the host side, you'll be notified of that mismatch. And that's it. So that's just a few initialization stuff with Nix. Okay. Once that's done, there's a range buffer that we allocate and we get information from the host from. And this range buffer is used by Nix. And the whole idea here, the reason why we need to be notified of the buffer range is the Nix API kind of dictates that whatever values it gives us from that range buffer, if it's enabled, then we need to call virtual lock on those IP ranges to make sure they stay present in memory. And if they don't, if something fails here, then we stop fuzzing with this user abort. This is just a pretty standard thing, part of the KAFL API we don't need to really worry about. We do something special here with set process working set size. And that's because when we're fuzzing WEVT service, another thing I do is I lock in the WEVT service, its code pages in memory to stop it from being paged out, primarily for performance reasons. It used to be a requirement, but I don't think it's no longer a requirement with Nix. So it's mostly for performance reasons now, to make sure it doesn't get paged out. But when you lock a lot of memory ranges into your process space, sometimes on Windows, you need to expand your working set size in order to support that. So we use this Windows API to expand our current process working set size to support locking in larger ranges of memory. And then we go to submit IP ranges. So when I said that Nix uses Intel processor trace for coverage, the thing about Intel processor trace, right, Intel PT, the way it works for coverage, it's a bit complex, but the focus on the part we only care about is we need to tell Intel PT the address ranges to track, right? We need to tell Intel PT to track coverage between certain addresses. It doesn't just track coverage across everywhere. We need to explicitly give it a list of address ranges and tell it to track coverage. So if we say to track coverage between 0x0 to 0x3000, if an address on the CPU was being executed at 0x4000, Intel PT wouldn't track that for coverage. If the CPU, was executing the address 2120, that is between 0 and 3000. So Intel PT would track that as coverage. So we have to tell it the address ranges to track. In our case, what do we care about? we're fuzzing WEVT service.dll. So we care about the address ranges in WEVT service.dll, right? In WinAFL, we told DynamoRio to track all the addresses in this module by passing, what is it, dash coverage module WEVT service.dll, right? We ran this command when we were fuzzing in WinAFL that told DynamoRio to track coverage for any address executed in that DLL. For Intel PT, we have to give it address ranges. So we have to find the code addresses in revt service.dll and submit them to Intel PT, right? We have to find the address ranges of the code section in our target DLL and submit them to Intel PT. And that's what we do. Hmod here is the result of load library on WEVT service.dll. And we know hmod is the base address of WEVT service. So what we do is we pass the headers of that loaded module of WEVT service to get the code section, which is the .text section, right? The reason why we're doing this is to save on space. So WEVT service.dll, right? It's a DLL. WEVT service.dll. It's a DLL, which means on Windows, it's a PE32 or PE32 plus format, depending if it's 32 or 64-bit. And it's got sections, it's got sections. One section might be the .text section, which contains executable code. Another section might be the data section. This might contain, readable and writable globals and, other sections, blah, blah, blah. There's no point passing Intel PT the entire IP range of WEVT service that contains all the sections, because it's not expected that a target is going to execute code from its .data section that's marked as read-write. Really, it should only be executing code from the .text section that contains executable code. So we get the address range of the .text section only and submit that. But, if for some reason your target calls virtual protect on .data to make it executable and executes code in .data, well, then you'd probably want to include that range as well for your tracing. But in this case, it's just .text, the executable section. So we find that section and we get its address and its size. We add the size to its start address, and that gets us the end. So we have the start and the end. So that's the range. We add that and submit that to Intel PT. Intel KAFL supports a number of ranges that you can provide, 4 in total, I think, 0 to 3. So this one, we're only using one of those ranges because we only need to track the start and the end of the text section in WEVT service.dll. There's nothing else that we care to track. So we get that, we submit it to KAFL, which tells it to track, any coverage between those addresses. We lock it in memory. We lock the text section in memory just to avoid page faults. If that fails for some reason, then again, we call abort, which tells KAFL something went wrong and stop. And then that all works fine, then it returns and we're done. For the submit IP ranges part. That means the ranges are submitted. Now at this time, we're ready to fuzz. So we tell it to prepare the payload. We call acquire, which takes a snapshot. That first kind of acquire release we did here, this is just a handshake. It's the first time we do acquire, and it's followed immediately by a release. It's just a special handshake. We don't need to worry about it. But when we call acquire again after that handshake is done, this will actually do a snapshot. So we're snapshotting at this point. At this KAFL acquire point, this is a snapshot. Which means once we start executing after then, the payload buffer will contain the input from KAFL. So what do we need to do? Well, we need to write that input to disk because the target, without hooking any of its functions, any of its disk-related APIs, it's going to be expecting to read from disk. So I have a hard-coded path here, C drive VHD ftarget.evtx. This is where I'm going to write the input to. You can change this to whatever path you want on your guest. And we call write payload file. Write payload file just creates the file on disk. If it fails, then we have to abort. If it was created on disk, fine. We write the payload data and the payload with the associated size to that file on disk, and we close the file. Our file's now been written to disk. We go to fuzz with that path. Fuzz. What does it do? All it does is it calls the target evt RPC register log query function that we're fuzzing with that path. And, we ignore any C++ exceptions. We don't care about them. We just return. Once fuzz is over, we call release, which will restore the snapshot. Well, it'll go to the next fuzz case. So the snapshot will reload at this location after the acquire here with a new input in payload buffer. We go write that new input, fuzz, and then restore snapshot. And we're just kind of looping in here, right? And if a crash ever occurs, it'll go to our special vectored exception handler that can report the crash. So hopefully that kind of all makes sense here. And in order to build this, I've got a little build.txt instruction here. Pretty much what you're going to do is you're going to launch a x64 native tools command prompt, which comes with the Visual Studio when you install it. I did Visual Studio 2022 in this case. You're going to go to where the files are. In my case, it is here. And first, you need to compile the assembler, the raw assembly. We compile the raw assembly using ML64. That compiles. That should give you a helper.object file. Then we compile evtfuzz.cpp with C++ exception handling support and using /mt in this case for dynamic DLL usage, which means that when you place this harness on your VM that you're going to use for fuzzing, you're probably going to need to install the Visual C++ x64 redistributable, I believe. This kind of Microsoft Visual C++ redist. There's the x64 version here that you'll just download and install on there so that it can run your compiled executable. But yes, we compile that. It's a warning here that we don't really need to care about, and that will give you evtfuzz.object. It'll give you evtfuzz.object. Now, as a last step, you need to link everything. So we use link, we use /debug so that it generates a PDB file, which will help with debugging your code if anything went wrong. We're using the console subsystem. It's not a GUI application. The outputted file is going to be evtfuzz.exe. It's going to link evtfuzz.object, which was generated from our CL here, and helper.object, which was generated from our helper.asm compiling here. And since we're using detours, we also link detours.lib, which is in this path for me, but you'll provide your own path to the libs x64 detours. And we're setting the entry point to wmain crt startup. And the reason for this is our evtfuzz main, if you look at our main, it's wmain, which means that the argv that we take is a wcar. pointer. It's a wide character pointer. It's not ASCII style. It's like Unicode style, UTF-16 style, WCAR. In order to get WMain to be executed with the WCAR, we set the entry point to be WMain CRT startup, which is a function in the C++ runtime. If you wanted to use just regular main and not WCAR, you would use just main CRT startup. But we're using WMain, so it's going to be WMain CRT startup. You can run this command, and that will give you evtfuzz.exe. Now, you can mount the VHD of your target and copy. You can grab evtfuzz.exe and evtfuzz.pdb, copy the exe and the PDB. You don't need the PDB, but I like keeping it with the executable, and paste it in the VHD of your guest. The VHD, you can just kind of like, let me do this quickly. You can right click a VHD and mount it. And with the VHD mounted, you can paste it in the guest. Or you can transfer it to the guest any other way you want. The main point is that in the guest that you're going to be using for fuzzing, in my case, I have got the C drive VHD folder. You've got the evtfuzz.exe executable, and you also got the associated wevtservice.dll that you're fuzzing. If it's the DLL on this same guest, I obtained it by doing just copy C drive Windows system32 wevtservice.dll into this current location, just so it's stored in the current directory of evtfuzz.exe. Now, I want things to automatically start fuzzing. Automatically jump into the harness and start running when this VM is booted under Nix. So what I mean by that is this. When our QCOW image is our target OS is launched under Nix, I want it to automatically launch our harness that's going to go into fuzzing. I don't want to have to SSH or RDP or whatever into the target OS running under QEMU to start the fuzzing session. I want it to happen automatically. And the way I'm going to do that is by creating a service. I do SC. This is under CMD, by the way, so not PowerShell. I'm just running CMD, just a command prompt. I do SC create evt fuzz service bin path equals to space C drive VHD evt fuzz.exe in my case, and start equals to space delayed dash order. If I run this, it's going to create the evt fuzz underscore svc service, and the executable that it's set to run is C drive VHD evt fuzz.exe, my harness, and it's going to start with delayed auto mode, which means it'll automatically start, but it'll wait a bit till everything else starts on the system first. And then what this means now is that when I reboot, if I run this and then I reboot my machine, when I reboot, this evtfuzz.exe will eventually automatically start. Now, I've already actually done this, so I don't need to do it again. But yeah, I'm setting it to just automatically start. With that done, I can just shut down the VM. Now, I've got the VHD. I need to convert it to a QCOW2. Now, you can install QEMU, right? You can build it from source, or you can just download a release build of QEMU. Windows or Linux, whatever you're doing this on. I'm doing this on Windows, right? So what I would do now is I need to convert that to a QCOW2. So I've got my I've got it's actually called verttest.vhd. You can ignore that name, but I need to convert this to a QCal2. What I do for that is this command. I've got QEMU installed in QEMU new, and when you install QEMU, it comes with QEMU-image.exe. So I call that. I use the convert. I'm converting from a VPC, which is the type it gives VHDs. So if you're using a VHD, you'd give it VPC here. If you're using VMware, which is a VMDK, I think you just put VMDK here. It's in the QEMU image documentation. I'm outputting a QCal2, and it's taking as input the verttest VHD, and it's going to output evtfuzz.qcal2. So once that's done, once I run that command and it's done, I will have the evtfuzz.qcal2 file. So now I transfer this file to my Linux machine that has Nix installed. In my case, if I have SSH access, I'll use SCP or something to transfer it from my host to there. You can use USB. You can transfer it over the network, whatever you want. You just need to get this image from your current machine onto that Linux machine that's running Nix. I've got a SSH session into that right here. Now, that means you would have this evtfuzz.qcal2 image. Now, I'm not actually going to fuzz this QCal2 directly. I'm actually going to create an overlay image and fuzz that to not touch the backing image. So this is optional, but I do recommend it. And the way you do that is I've got some helper text here, but you create an overlay using this command. So I've got QEMU installed on the Linux disk, on this Linux host as well. And you would run something like this. QEMU-image we're creating from a QCal2 to also a QCal2. But it's going to have a backing image. And that backing image is the evtfuzz.qcal2 that we transferred in. And the new image that we're creating is evtfuzz_overlay0.qcal2. So I'm creating an overlay over the backing image that we just transferred. And then that would give you these two images. Well, you'd already have the evtfuzz that you would transferred on, which is the large one. But then we just have an overlay, which is much smaller. And we're going to be fuzzing with the overlay. So now that that's done, we've got the disks set up for fuzzing. I can go into the KAFL main repository here. And what you'd normally do now is go into KAFL folder, subdirectory in there, and you'd do make env, and then you'd have this env.sh file, and you'll do source env.sh. That's what you would do. Once you source env.sh, you'll be in a venv a Python virtual environment. Once you're in that Python virtual environment, maybe I'll do it. Let me go screen-s KFL test. I just want to create a screen. Wait, am I in a screen session? No. Screen-s KFL_test. What you do is do something like source env.sh, and now you'd have this .venv on the left there. And now we can get ready for fuzzing. I've set up a KAFL configuration for fuzzing this target. I've got it in examples Windows_evtfuzz, and you'll have access to this file. Really, there's just two things we care about. The YAML file that specifies the configuration for KAFL, and the seeds folder, which contains inputs to start with. So that, you know how we exported the EVTX file as an initial input that we used for getting started fuzzing on What the Fuzz or WinAFL? That's the file that you would put in seeds. I've actually got multiple in seeds right now, multiple files. Um, but that is where you would put that initial input to start with. KAFL.YAML contains the configuration. For example, we're saying that we're running, we pass through QEMU base, which specifies some configurations for QEMU. Specifically, we've got -VMX here. And that's because we want to fuzz without virtualization capabilities in QEMU. Because we're not fuzzing a hypervisor, right? If we're not fuzzing a hypervisor, I don't want QEMU to boot my Windows guest with hypervisor or virtualization enabled, because then perhaps my Windows guest would be running Hyper-V and stuff like that under it, which would just incur performance impact. There's no need. We're not fuzzing a hypervisor. There's no need for virtualization extensions to be present in our guest. We're not using the network, so we don't need to emulate the network. We have things set up so that they'll automatically start fuzzing at boot time. We don't need it to have a display. I'm giving the QEMU guest 4 gigs of RAM. The path to my QEMU is here. Now, by default, I think when you set up KAFL using make deploy and that it will build QEMU for you, you don't need to do it yourself. But if you wanted to do it yourself, KAFL uses KAFL.QEMU. There's this KAFL.QEMU repository from Intel Labs, and this is the patched QEMU that KAFL uses. So you could clone this, and you want to switch to the branch called KAFL_stable. When you're in the KAFL_stable branch, you'd go into the repository and you just build it. Building QEMU. The instructions are here. It's pretty straightforward. You just go in and you run compile QEMU nix.sh with LTO if you want link time optimization. Or you can provide it static. I built it static. So did I include that in here? Don't think so. But when I built it, instead of providing LTO, I provided static. And it just built a static QEMU. But that's it. Building it is very straightforward. You just need to make sure that it's the KAFL.QEMU repository and that you're on the KAFL_stable branch. If you've done that, then it should build under that repository this x86-64 soft MMU folder that contains this QEMU system x86-64 executable. And I'm just telling KAFL to use this QEMU emulator that I built. But again, if you just run make deploy in KAFL, I don't think you need to build KAFL QEMU yourself like this. Make deploy will automatically build it and you don't need to provide the path. But I explicitly built it and I provided the path. And this is useful as well if you made some additional changes to QEMU. You pass QEMU image, because in this case, we're using the QCal2 overlay to fuzz with. So this is just the path to that QCal2 overlay that contains the guest that we're fuzzing. It uses the home environment variable because it's in my home directory /code/ these folders to the path of the QCal2 overlay. You'll replace this with whatever the path is to your overlay. Just some extra commands to QEMU you don't need to worry about. Seed directory is the directory that contains our initial input seeds. That's in my KAFL examples, Windows EVT Fuzz seeds folder. Some configurations here. Red Creen is a special mutator. I have that enabled. Grimraw is another mutator that requires additional configuration, so I've got that disabled. I'm fuzzing with 8 CPU cores. That's what this processor is here. Processors. I have it set to 8, so it's just going to fuzz with 8 CPU cores. You can adjust that to whatever value you want. There's a Redamza mutator. I have that disabled. And I have logging enabled. With all that done, I can run KFL fuzz and it will do its thing. Let's do that. But I already have that on another screen session. So I'm going to go screen -r kafl. I'm going to stop this fuzzing session. Okay. Now, when you're fuzzing, there's a couple other things to keep in mind. So what I've got here is kafl space fuzz starts a fuzzing session. Now I've set soft and hard timeouts. So what this means, --t-soft 45, means that if after running for 45 seconds in a fuzz case, if we have not hit a crash or the end of the or the restore function or anything, count it as a timeout. That's what I'm saying. I don't even need the hard, really. I can remove that. But really, we're just saying with the soft command here that 45 seconds is our timeout. If a test case takes longer than 45 seconds to complete, assume it is a timeout. I'm being very generous here because when I had it be a lower number, I found that I was hitting some timeouts. But when I raised that number, it eventually actually resolved and went to the next input. So it did reach the end of execution. I just wasn't giving it enough time to complete. And perhaps that's because I hit some sort of function or set of functions in the target that just took a while to process. So I'm being very generous with the timeout here. --purge is just saying if there's any leftover stuff in the fuzzing folder from a previous fuzz section, delete it all. If you wanted to resume off a previous fuzzing session, you can do --resume. But I'm starting fresh, so I'm doing purge. You can also do trace, and this comes in handy when you're visualizing coverage. So when you visualize coverage, what it'll typically do is it'll rerun the inputs into your fuzz cases and log out the traces that you can then use to visualize coverage. If you pass --trace when you start the fuzzing session, it'll automatically save those traces and you won't need to rerun through the inputs when you do kafl cov, which is the coverage command. So this trace, it's not required. You don't need to put it there, but I'm putting it here. Another key thing that I'll just reiterate is since it's going to log down, its coverage isn't going to be in the form of module plus offset, right? When you get coverage output from kafl, it's not going to be WEVT service plus 0x1331 that says offset 1331 from WEVT service was executed. Instead, you're just going to get the raw address like 7FFF78008020. So how do you actually visualize this? Well, if you know that WEVT service is loaded at base address 7FF78000, then when you see this address, you know that this is offset 20 from the base address, which means you know that this is WEVT service plus 0x20. And then you can visualize that in Lighthouse, in Ghidra, things like that. But this means that you need to know the base address of your targets that you're interested in, which is why in the harness, when I load WEVT service, I use hprintf to pass the base address to kafl's output so I can, for my own record, know what the base address is. This comes in useful when we visualize coverage. Let's see that. I'm going to start this fuzzing session. It's booting the VM and it's going to wait for fuzzing to start. It did it 8 times there because I've got 8 fuzzing nodes, but now it's running the QCal2, and because we created the service to auto start, this should auto start fuzzing because the service will automatically start my harness, which will start fuzzing. So I just have to wait for that to happen. Now, obviously, if something's wrong with your harness and it doesn't execute properly, then you're just going to be stuck here waiting forever. So you might want to do additional verification that your harness actually boots up and runs up until the VM call in the in your VM before you start trying to fuzz with it. Of course, when it actually executes the VM call, if it's not running under KAFL, it'll probably crash because there's nothing to handle that VM call. But you can just attach a debugger and make sure it gets up to that point. Okay, you can see here the hprint, and look, the base address is here, 7FFA. Okay, I lost it, but it was there. 7FFA something, something, something. One thing that I could do is probably log this output to somewhere on disk so that I don't lose it on my SSH screen session when the screen scrolls a bit too far. But it did print off the base address. If I save this output to disk by using a redirection, then I would be able to just cat the file and get it, which is probably what I recommend. But yeah, you'd know the base address from there. And then now it's just printing off fuzzing stats. But we don't need to view fuzzing stats like this. Leaving this running by just detaching from the screen session, it's still running. But what I can do is go into the same folder with a virtual environment as well, right? Sourcing that file, that env.sh file. I can do kafl space GUI. And with that, it gives me a nice GUI. It shows at the bottom here, the workers, and what they're doing. It says here that there's 8 out of 20 workers. So I've got 8 workers, 8 fuzzers. They clearly don't all fit on this screen. So it's only showing workers 0 to 4 here. It shows the execs per second per worker. And at the top here, the current execs per second is total from all the workers. So you can see with 8 workers, I'm getting close to 1,000 executions a second. Mind you, this is working with disk. Every fuzz case is writing the input to disk, and then the target's reading it from disk. Shows CPU use and RAM use. Here, it shows the findings. Regular are just inputs that stress new paths. Timeouts are timeouts. Crashes are crashes, right? AdSAN are crashes from address sanitizer. If you're fuzzing a target that uses ASAN, you have to handle that a bit differently. Here, it just shows the different mutation methods and which ones contributed to findings of inputs. How many basic blocks were found from fuzzing so far with coverage? Yeah, that's kind of the main points. Your runtime, how long you've been fuzzing for, stability, that sort of thing. Yeah, so that's it, fuzzing away. Now, with it fuzzing away, what we can do is, well, we want to visualize the coverage in something like Ghidra, or IDA, or whatever. So what I'm going to do, let me get out of this. Just go to test. What I can do here is I can run kafl cov. Dash resume, I think I need to do. Maybe not. I think I need it. I can't recall if I need it or not. What did I note down? Possibly. Let me run it. Ah, whoops. I'm not sourced into there. Green-ls. Script. Oh, I did not do source. I can do source env.sh. Okay. Examples, Windows CVTA files. Here, kafl of zoom. I think what I may need to do is stop the fuzz session. I've got the fuzz session here. I'm going to stop the fuzz session. Control C. So I think when you stop it, that saves the IP range information. Now I can do kafl cov -- resume. Okay. Now it's going and it's generating some trace information from the coverage. Done. Now under dev/shm, now this is the default work directory. You can customize this yourself, but it's by default in /dev/shm/kfl_ your username. My username is Smith, so kfl_Smith. And this contains a few things. Snapshot is all that stuff. Corpus, right? If I go on the corpus here, it's got the crashes, any regular inputs that generate new coverage, timeouts, etc. And all sorts of things. If I go under traces, there's a few trace files that are compressed. The documentation on KFL will have information on what these are. We're mostly interested in edges unique.lst. The unique edges that was generated from the KFL cov command. We can visualize this straight in Ghidra using a Ghidra plugin that's included with KAFL. Though I've got mine slightly modified. I believe in KAFL, you go under fuzzer and then scripts. There's a few scripts here: Ghidra run, Ghidra cov analysis, dump blocks, cov plot, PT. Actually, I think this one's mine, and a few others. Ghidra cov analysis is what we're going to be using, but I've had to modify it to work with Ghidra 11, I believe I'm using right now. So what you're going to do is extract this. I'm running it on Windows. And under traces, copy out this edges_unique.lst file. And I've copied that out to my Windows host. And I've got Ghidra here running on revt service, right? I've got it loaded up here. And I'm going to go to Windows, Script Manager, and I just create a new script. And the script that I already created, what did I call it? Did I call it KFL? What it's something. And I already created it. Don't know where I put it. By the way, doesn't matter. You just create a script, Python script, call it whatever you want, new script.py, KFL 12.py, or whatever. It's here. Now I need to view the content that I'm putting in there. Code Ghidra scripts, this. Copy it. Paste it. So this is the script. The changes that I made, I'll kind of go through. There's only two changes, I think. One is there was an import here or something. Some sort of list. I forget what it was. But that import was broken on Ghidra 11. See if I can cat Ghidra cov fuzzer scripts. Let's see if I can find it. This. See this from ghidra.program.model.listing import listing stub, which is above flat program API. And here, there's no listing stub. So it was an unused import and it didn't actually exist and caused errors when I tried to run it on Ghidra 11. So I just deleted it and that's fine because it's an unused import. The other thing I did is the path. You give it a path to the edges unique.list. By default, it has a Linux path, something like /temp/edges unique.list. Since I'm running this on Windows, I just gave it a Windows path to where I've got that edges unique.list here. It's just hard coded in there. And that's where it's going to find the edges unique.lst. That's where I placed it. Those are the two changes I made. You can make those two changes yourself. With that there, and that pasted into here, I can save the script, then I can just run the script. Now when I go to Hydra here, it's running the script. Oh, sorry. One thing I need to do is you need to rebase your program to match the base address of your coverage. So if I go window, I go memory map, there's a home at the top right here. I click the home, and you want to set the base address here to whatever the base address was that you logged when you did the fuzzing, right? You know how we did fuzzing and it printed off that base address? You're going to put that base address here so that it matches the trace file from Intel PT. Once you do that, then you can run the script and it'll code coverage things so that when you go to the functions it should be hitting, like EVT RPC register log query, you'll see that the disassembly blocks here are colored. It's highlighted all the basic blocks in the coverage that have been hit from your fuzz cases, from all your fuzz cases combined. It's the coverage of all your fuzz cases. And now you can view what coverage has been hit, what coverage has not been hit, and assist with analysis this way.